possibility to walk any days here. We have lectures. My course, I think you have a short summary. My course is at all about polymerization reactions, about radical polymerization, ionic polymerization. That's my subject in this field. I worked chemical faculty in Vilnius University, polymer chemistry department, and here I am invited special for this course, a very short, many things explained for you about free radicals, mechanism of polymerization, ionic polymerization, stereospecific polymerization, copolymerization, multipolymerization, these questions. I think in these hours I have planned 20 hours. We can resume any steps. I think maybe better understand in this subject as polymer chemistry course. I know too that you are third and fourth studying years. I have your names for remember. I can bring to Lithuania, and your colleagues, teachers, have to say me that you are all who is here in this auditorium very good students and with good kindness, good possibilities. That's very glad to see you, and I think we can together understanding most all in these questions. When you wanted anything, ask me. We can after lectures or the institution. In the time you can ask me. I wanted in this case by beginning excuse you while my English is enough poor. This lectures, this course, I had first time at all in English. In Lithuania, in Vilnius University, we teaching on Lithuania, or exactly Lithuania language. Lithuanian languages, I think you know anything about that. Very old Sanskrit languages, and not similar as Suomian, Finland, or Sweden, or other languages. And I can say I sometimes change English words with German words, while for me it's a little easier of Germany to speak at all. Wenn Sie haben Möglichkeiten oder Sie kennen anything auf Deutsch, können Sie fragen mir auf Deutsch, wir können auch unterhalten. Das ist für mich mehr besser. But I know that here I must to speak on English. And I think we can anything understand. When you cannot come any questions, not understand, please ask me. We can friends to be here in this auditorium in this hall. Yes, this is introduction, my short. And now I want first lecture for you. Begin today about free radicals and initiators for radical polymerization process. This is the first part for this course, and for this we can begin. Yes. I know you are ended organic chemistry. You know organic chemistry very good. And now you begin physical chemistry course. Here in polymerization processes, in polycondensation processes, there are many questions on organic chemistry and on physical chemistry, kinetics, thermodynamic questions. But I think I was asked that I must, as possible, a little to speak about kinetic and thermodynamic in high material. This is the problem. As possible, near this subject, near to organic chemistry. Good. Right. Now I can speak about free radicals. Now, historisch, very short. Schon 90 years have elapsed since the discovery of free radicals. This was 20, this is one Americana, and from 90 years as he first had to say that carbon is usually is covalent. Yes, it is from Kepler time. Do you know this is a classical rule? But these questions, that was on Kepler. And from Gomberg, excuse me, Gomberg. Yeah, exactly. Very famous American physical chemist at that time was. He said that exists just carbon, this anti-electron gap. Then we have examples. Methane, yes, methane. And then one hydrogen abstraction, it became such free radical. We can write, usually that's right, in that case. this free radical. But 1900, at that time, this was not speaking about methyl or methyl in English exactly, radical. Now we know just kind radical is very activists from all free radicals now is such radical, very active. This electron is not stabilized, but at that time, or what causes this problem that is possible carbon equivalent was as Emil, you know, right in search to show immigration. That's the same. This was my Homberg. Yeah, became very tough. By heating. Activation energy is necessary for this bond. This bond is enough weak. We can return a little later to show the same. The formation of free radicals. But that was 90 years ago. First question for what begins these problems from Bomberg time. This bond is for destruction, for decomposition, is possible by activation energy, 11 kilocalorie per mole. This is enough weak bond. Can you compare now from this table, let us say, what is necessary activation energy, how large, for abstraction, for example, Kokoloje, one hydrogen abstraction is necessary 77 kilocalorie per mole. This bond, when decomposed, rupture, destruction, is necessary 68 kilocalories. And compare the electron at all cases. That is named free radicals, all free radicals, and hydrogen too, free radicals in this case. Can you see a tiny bond is activation energy 84 kilocalories per mole, and this is very active. When we are speaking about activity or possibility as free radicals is enough large difference from these radicals. Now I can say last example, methane. Methane from such kind. For example, such kind. Pure organic chemistry. But when I want that abstracted, this is tertiary hydrogen, carbon. Secondary, that is primary, yeah? In this case, you're right, yes? Remember you, organic chemistry. At what hydrogen can is a abstraction of this example. No, I can, I will not examination you. I want you remember. But can you see here? This is the primary hydrogen and this is tertiary hydrogen. No, hydrogen, say it cannot be, I mean, say CH, this bond. Primary, secondary, tertiary. But can you say? Primary, 102 kilocalories per mole is necessary energy as this bond rupture. And that is 91. But that right is for me, and this is enough, not easy, but enough easy. In such kind of destruction is more easier, or this is not so easy, but 68 kilocalories, it is 11. What compound, this symmetric molecule, ethyl ethane. This bond is weaker, while this p electron on benzene ring is conjugated. This system system, p electron, and oscillated electron, p electron, oscillated, moved in all carbon atoms. And this bond is more weaker as in this kind. No, after this. We can, yes, compare toluene and ethane. Here is alkyl, here is aryl. And so large difference in bond energy. But here the same as we have to say about this kind. This p electronen, 6p electronen, in benzene, they oscillated and this conjugation with all system, with not with 6 carbon atoms, but with 7 carbon atoms. Electron moving, oscillating. And at that kind, or that this hydrogen is not so strong in bond with carbon. And we can abstraction hydrogen easier as in this case. Or in this case. In this case. No, and at last, this example is very old for what they can, that carbon can be not quadrivalence, can be trivalence with anti-electron one. But here is conjugated molecular very large conjugation, and all electrons is in all system. And this bond, this is such two electrons, covalent bond. Yes? They are in all these systems, and moving in oscillation. It's two. And this bond is very big. Such and now well, here we can say that the term radical will be taken to refer to an atom or molecule which contains one, sometimes more, two unpaired electrons. And this definition will exclude atoms, for example, transition metals. On table, transition metals which have two unpaired electron, but an inner shell. That is that kind transition metals, two with unpaired electron, but not valence electron unpaired. They are not free radicals. Radicals must be molecular of atoms, contains unpaired electron, valence electron, and covalent bond. Such is. Can say that free radicals usually have not electric charge. They are positive charge. They have not positive or negative charge. Such a species is highly reactive because of its unpaired electron. And usually you can write, for example, the electron can write thing. There are two features or two possibilities to write formulas. One is Lewis formula. This is in English Lewis formula. And to write, for example, such kind. And usual form, right, and the complete regard, you show only unpaired electron, and such is more usually right, but free radicals. And now I want to return again. This is historical, a little explain how to begin with radicals. And now in organic chemistry, do you very good know this reaction? You remember maybe about three radical process by radical mechanisms, halogenation, chlorination, bromination, fluorination, and other organic reactions. Very easy process, coupling process, without activation energy. Activation energy in this case is equal 0, null. Like coupling such kind free radicals. At all, coupling free radicals by the combination process is not necessary activation energy. Only for this proportionation process, little is necessary activation energy, about 1, 2, or 3 kilocalories per mole. Industrial, commercial polymerization process, useful initiators they have activation energy, bonding activation energy. Here we can say what place, what bond is weaker for this all compounds. You for organic chemistry, do you know very good? This is activation energy in this interval. Right here, we can 4 and 19 multiplied and became 168 and 105 kilojoule mole. This is in C system. You know. Yes. Such kind of compounds we can say, and usually is in practice as initiators, industrial initiators, commercial initiators, is such necessary. For example, here is right benzoyl peroxide. Usually in Finland, your industry use sometimes this compound as generator from free radicals. Again, when rupture this bond enough weak by this electron and covalent bond is in conjugation, in oscillation in this part of molecule, while it is possible in this p electron and this, and at all this electron this is spent not always in that part, but sometimes is oscillating. For example, yeah? And other. You can remember, this is benzoyl peroxide radical from benzoyl peroxide, but that is for ethyloxide radical. What can you say about such things as chemists? What reaction is possible? This bond and this bond. In this case, we can write plus CO2, yes? CO2. In such case, 6 free radical plus CO2. What difference, let's say, what reaction is easier and possible at all? When such kind of reactions is possible in solution, by this destruction we can get very active free radical, methyl radical, activists, most active radical. And it is very good in rapid polymerization we can. And with such reaction, this free radical is very weak. Do you know? You can understand now. Yeah? While this free or unpaired electron is in conjugation in system conjugated. And, or we write such not fixed, it's radical. This free electron is in conjugation and cannot begin polymerization process, not can begin that reaction. Or I was to write here with R use monomer. But I can say such reaction is at all most in in our situation, the polymerization process, what is industrial or the commercial or the laboratory, is not this reaction. Only this is the most sense. This radical is enough active, but not so much. But that reaction is very, very easy to go, and it's possible. What is, we can compare organic chemistry problems in radical process to your knowledges you can use. You can understand process of radical polymerization. This activation energy is largest for initiators decomposing by homolytic destruction, and smallest activation energy necessary for reaction of termination. And at all, then divided in 4 steps of polymerization process. Some net reactions activation energy is about 15, 17 kilocalories per mole. Such, and I want to note for you that often process to terminate recombination by termination process. Recombination. And disproportionation process is possible when you do this polymerization by high temperature. Then by lower temperature, as possible, then eliminate recombination process. For this is necessary used as possible lower polymerization temperature in practice. Not for only for that. Is many purpose and other is necessary that polymerization process is necessary used as possible by lower temperature. We can see later. And I think when our order is very strong, as in Finland say, that must be make one rupture, one pause, until the next picture. Entr'acte. Sì. I want again repeat for you such process of polymerization for steps begin from fast initiation of periodical polymerization. I want here to show for you kinetic of each process, of each step. The test was at all about each step. Now, again, we can see first initiation destruction and then initiation process with small constant of initiation. Transition state, can you see? This was double bond abruption and first such kind and transition state and then covalent bond, and next step will begin propagation. rate sometimes to write R small, sometimes when small, and sometimes large. Velocity, rate, small rate, or such, and rate. Such for us, it's possible to change with R, with free radical. We will not use such marking. R in our cases, or R, for example, one is relation of constants in copolymerization we use, and such, for example, copolymerization, or such. Next, next lecture, velocity is very good for us. Velocity rate, and large way, this is volume, can be changed. This is not good for market. That's all. When you read literature. Initiation rate for constant rate constant for homolytic destruction. F. Then you see how you see enough new efficiency factor. What then you here is right. Homolytic rate, homolytic decomposition rate constant. That from organic chemistry, I think, do you remember that? That activity from such primary radical, free radical, and for example, such, or activities is the same, reactivity from free radicals. The same as from, you can remember, for example, such, and very large, for example, this carbohydrate, and for example, only in practice, functional groups activity is the same. You remember, in practice, you must always in practice. In that do is in practice. Theoretical, maybe a little there are. For and so yes, many things I speak maybe too much more as you can better I self. Yes, and to write any nouns from velocity rate or rate constant of propagation. Next lectures we speak about copolymerization process and Saturday, and about the activity of monomers and radicals, and then we can better understand the copolymerization process about reactivity. But now when we have here propagation process, just Kapel, rate constant of propagation. This means when in system there are 1 mole concentration reactants, I can read for you, for your better understanding. For example, styrene, as monomer, KPM, 90 liters moles per second. Methyl methacrylate. I not this monomers, I think we will know or not know next time, next lectures we will write. Now, 300. Methyl acrylate. 720. Vinyl acetate. Vinyl acetate. 1000. I can write here as a dimension by C system. Literally is unusual now. The same. On the, from this rate constant, you can understand what from monomers or radicals in polymerization is more reactive. Yes, very important. Oh, and a little about a little more the propagation step. When we can calculate velocity of propagation process, elemental reaction, propagation, not brutto of growing macromolecules, but on such a step of propagation. You remember such a reaction? Your conspects in letters former lecture. Yeah. And that eventually you remember it way. And then you know, can you measure, can you find that amount or velocity of initiation, such monomer concentration do you know, that can you calculate it from polymerization process. It's enough. Is it that made? And then can you calculate it elementary reaction of growing process, of propagation process. You can remember that. Captain on the reaction and concentration. And it's very important things for studying the kinetic of propagation process and at all about radical polymerization. And then we later were speaking about copolymerization. It's very important to know such process. And here is in other graph, in coordinates a little other. But for such equal when we use KH, KF, efficiency and velocity constant of homolytic destruction of initiator. This is same as KE. Or here, this methyl group hydrogens is not, bond is not so strong, and so they didn't die your and plus new radical as name. Let's name the chain transfer to solvent. And that is solvent. We write constant. Transfer. Kappa. Get transfer polymer, that's CP, and larges. Usually, this constant must be as possible smaller. But here, in vinyl acetate phases, by polymerization, is enough large. Then you cannot see that in your prospects there are CM and vinyl acetate transfer. Okay. Ten minus 4. That's enough large, and that is cause, can one say, here you can read, it is chief effect to cause chain branching when transfer occurs to polymer. Chain transfer for such, you can write but when chain transfer occurs to macromolecule, to polymer chain. Here is polymer, polyvinyl acetate, for example, and here is growing radical. And in such case, this is possible chain branching. Chain branching to polymer. This understanding, I think, is so. New radical. I can write that you became such O, say O, such radical of macromolecule, and here begin is possible beginning new reaction, for example, M. In polymer system, okay, such branching macromolecules is possible. And such example is maybe you know about that polyvinyl acetate is not possible to get a large average molecular weight. Usually polyvinyl acetate is about 100,000, 200,000 average molecular weight. This is for polymer, for macromolecules is not so large at all. Usually many polymers have average molecular weight, polymers, macromolecular weight, many hundreds, thousands, sometimes millions. And for polyvinyl acetate, it's not possible. This is one. This is one cause why it's possible branching reactions due to chain transfer, such kind of reactions. And once more, second problem that branching reactions we can get. But for example, polyvinyl acetate always is branching macromolecular, not line. And that line, such kind, and branching, such kind. And physical properties, physical mechanical properties is very different in such kind. Then you get macromolecules and polymers branching or line when you compare such properties. Here again to see anything is possible the same principle. Here is one monomer mesacrylonitrile or nitrile. Can you see? With methyl group at alpha carbon atom. The same, this bond carbon hydrogen is weaker, not weak, and there are oscillation of electron system, polymerization. Branching polymer. And such kind of polyethylene is low density polyethylene and high density polyethylene. By similar naphtha catalysis. Here, under pressure and high temperature. Here, without pressure, without high temperature. This is very important. Physical properties for these both polymers is very different. Technical, technological uses, manufacturing, this is very important. That's when we spoke about branching of polymers by synthesis and by using coordinating possibility in having catalysts. Now, in each year, let's say statistical, approximately maybe 12 cents to get about 500 royal. Many kinds of catalysis systems. I see another things that is a new discovery. And research chemists, many laboratories, they say in Neste, they developed, improved such process, and they research new systems, what is possible better and better to move on to point from this research. It's very important, and we can later to see how it's difficult understanding all. And here about first about metal transition metal activity, efficiency. It's decreasing. Can you understand that, Mark? This is tetrachlor vanadium, or the vanadium tetrafluoride is for this group metal is mostly reactive for polymerization. What means reactivity or efficiency? This is not so easy, not so simply understand. Maybe this question we can calculate it or interpret it as velocity rate, for example. In radical polymerization, we had spoke about efficiency from free radical, for example. Yes? What is more reactive, or what is more stable and less reactive. This here is reactivity ratios and stereospecific properties from efficiency. And here spoke not exactly about reactivity ratios, rate of metals such salts, but about efficiency to stereospecificity or symbiotic or isotactic or atactic polymers could get by using such metals. This is more efficient as vanadium oxychloride. The first system was for Ziegler Natter. At that time, by discovered this tetra such was carbon. We can write such. There is one bond, covalent bond, two covalent bond, second covalent bond, third covalent bond, and carbon is as four valent from Kokoloje, you remember maybe, or this first was as dogma for chemists. And here, in this case, we can write that it's the same, we can write these two. Yes? This is minus. And for such atom for carbon, we can write electron configuration and electron positions and such. That means carbonium. That is this positive charge. Can understand as three valence, yes, and charge. Yeah. Now you means about such from all your knowledge is about organic chemistry. What ion and what atom is more stable? Then we have such system with 8 electrons, generally, yes, for atoms, and here we have outside 6 electrons. Carbon, carbonium, ion, maybe more active, understand? less stable. No, can you remember this? By anionic polymerization, former lectures, we have spoke about very stable anions, living polymers, or life polymers, living polymers, lebende полимеры, Aldo sagt man, живущие полимеры, on Russian language you can say. Yes. This is very stable. Understanding the system and is enough stable. And with carbonium ions, you cannot yet synthesize living polymers. But activity, such ends of growth, growing chain, is very active. From here, one conclusion can be made that ionic polymerization at all is, by velocity and calculated, is more larger rate and more quickly process. And from here we can say that not so easy calculated, not so easy studying elementary reactions, as for example in radical polymerization. We very sharply, very exactly can measure and calculate it, initiate a step after propagation step, termination, chain transfer, with rate constants to measure. All is possible related. In ionic polymerization, such kinds of measurements is very difficult. Speed, velocity, rate of reactions, and all steps. There are steps, understanding, initiation steps, dimerization, propagation, and sometimes termination axis. And sometimes chain transfer on the, for stereoregularity, for coordinated systems is not possible chain transfer, and branching is not possible. But very quickly, not possible. And from here, for kinetic specialists, for kinetic measurement, it's very difficult to find equals, reactions, units for calculating elementary reaction. And we, for ionic polymerization, we get not so sharply, exactly equations for each step, but only about approximately assumption in such, and in ionic polymerization is the same as in anionic. We cannot write exactly equations. By each reaction kinetically have many specificity. This is dependent on monomer, dependent on medium, on catalyst, no? And from other things. And that is hence for this ionic polymerization sometimes chemistry is not so easy, not so like as research and work. They work with radical polymerization. Yes, we can continue. Here's the chain. Yes, this is clear. I think monomers at first. About monomers, short, after about catalyst, and then about mechanism. It is very active. Compare with free radical anti-electron. It's an understanding. standing. Yes. And from not monomers, one group vinyl agens. Agen group bonding through oxygen and the standing, and here is vinyl. Here is maybe but such kinds monomers by radical polymerization too is not possible polymerized. By electron donator, cell groups and electronin. Enough four electron can you see here, and it's not so easy by radical polymerization. It's impossible. From you can say for aldehydes, for example, aldehyde polymerization. This is polarized to double bond. That means can very good polymerized by cationic mechanism. But can you say for me, or I can ask you, maybe that possibility here is an anionic polymerization maybe. This double bond is 1 plus 1 minus very polarized. And when it's very polarized, then it is possible by cationic mechanism, but it's similar, like or equal. It's anionic polymerization. Understand? Yes, that is, you are right. Yeah. It's possible, it is possible polymerized by anionic and by cationic polymerization method, but not by radical polymerization. With free radical, it's not possible. From here, what conclusion before Tauco, that when we have possibility to use such methods, radical polymerization, anionic polymerization, cationic polymerization, and coordination, stereospecific polymerization, we have many possibilities, many compounds, many monomers, and very large number of monomers is possible used for polymerization process. But when we know only radical polymerization, as for a long time this was only radical polymerization. Ionic polymerization about as free division, own division from polymer chemistry. We have not so long time, about 1940, 1950 years. And radical polymerization is from 1900, 25 years from first works from Hermann Staudinger as father for polymer chemistry. He was first. For such is our course. The lecture about cationic polymerization. I want to show for you cationic catalyst. Wanted advantages for radical polymerization. Radical, possible, such easy and get such radical. This anti-electron is very weak and not so electrophilic. It's enough saturated with p electrons of nuclear, of ring, phenyl rings. It's not used when you want to get a large molecular weight polymers by radical polymerization. And cationic polymerization very good. 12 would write is necessary, while polar molecule is not so easy to write, and sometimes water, the rest of water remains. This is difficulty at such. Now, other steps, propagation, chain transfer, termination, and technical useful uses of ionic polymers. I think maybe next time after excursion tomorrow to Tampere, and Saturday morning we continue, and we have next time next lecture this condition process, polykondensation process, and that I think maybe from my side finish. And Saturday, and today we will spoke about polykondensation reactions, that the first from last lecture. Anything continue. Just what? Then I think that is yes, we have a mechanism of cationic polymerization by steps. We ended understanding, yes, but this is must you remember always to attention. This dimension is more second, and rate constant is liter from mole second. This is second order reactions and understanding such dimensions. And here rate is large, compare with rate, then average polymerization degree or molecular rate, and then we write such as monomer. That is monomer molecular rate. Then multiply this number and monomer molecule, then we have average molecular weight. And average molecular weight by statistical, then with enough large distribution. Then we have in process, for example, for radical polymerization mechanism, by free radical polymerization. Such distribution of macro molecules at average we wrote that and such maybe no, for example, radical polymerization. Schultz factor in chemistry. When it's one, that is all molecules is the same length. The Schultz factor and W is U. This is weight, molecular weight, and number molecular weight. And in such cases. It's very important for practice, for industrial, for manufacturing of polymers to get to form such polymers. And as possible, more distribution, verified molecular length. It's not so good, but the chemical properties is very differences for such. But why is possible to get such molecules with very small, very narrow distribution of molecular weight? When speed of polymerization or rate of polymerization is as possible larger, then statistical always, not always, but statistically it's possibility, more possibility to get it. But then we have such situation, this is rate, yes, of polymerization. Radical polymerization, rate is small, anionic a little more, much more. Rate of polymerization, and cationic more as anionic polymerization, rate of process. That can you understand from here and compare with such situations that by cationic polymerization we can get with distribution near such. So, for example, practical, this is theoretical maybe, but in practice we can arrive minimum such. One, and for example, this brilliant condition of distribution, understanding. Then here is a little less, or larger distribution, and by radical polymerization, where in cases that's dependent from conditions of situation for polymerization, we can do such, and most right. But such relation, such number for the polymerization. So such understanding that is extremal variant and must maybe wrote this for polymerization for industry is not good. Mostly this is 1, 2 in praxis using and choose conditions for continued process. This is short about such problems that all compare any methods for polymerization process. And now we continue our steps of cationic polymerization. This very active chain end. This rose and bear positive charge. Yes, can you send to read the sentences, initiation reactions occur simultaneously with the propagation steps? This mostly is very difficult difference as for example, by radical polymerization, there are very easy differentiation process, and calculated initiation rate is very easy. You remember maybe by inhibition method using inhibitors. And in ionic polymerization is very difficult, such calculating and measurement elemental reactions. Rate of elemental reactions, constants of rate of elemental reactions. By rate at all, summary rate, the speed velocity of process is very large, very large. Many times larger or higher as by radical polymerization. And statistical then is simultaneously occurs reactions, initiation, propagation, sometimes elimination. Yes. And very difficult, for example, propagation reactions step. Propagation concentrate. Here there are. What to write? This is not necessary. No, at all. We can write. For example, such. But there are co-catalyst concentration. It's not necessary to write sometimes, but to know. And such situation complicated. At all, I can say here in this equation, here, can you see? Right? Good. Here is concentration, summary concentration, and all what we have is a system. This means as complex growing chain concentration, this counter-ion. But counter-ion is, we have, for example, such. Co-catalyst. This is concentration must be co-catalyst enough verified. Mostly theoretical, such relation must be equimolar. Equimolar as 1 to 1. Molar relation. But it's a very dangerous rest of moisture, of water. You know, our process, anionic polymerization process, the same anionic polymerization process, must be in condition very dry. Very dry. And then you use such reaction is a possibility that such complex yields exactly 100% must be. But theoretical is possible, but practical that is not always reactions is possible to get 100% in yields on conversion. That is very, and the rest This destroyed your catalyst system, and rate of polymerization comes very quickly low. That's always used about such relation. This relation, I mean, catalyst and co-catalyst. Catalyst, co-catalyst. That is always is not danger from the rest of water. But for kinetically or calculating rates or constants of rates, this co-catalyst must be in head. We must thinking about such thing. This reaction is equal when we have exactly catalyst complex as proton donator only in system. And this complicated possibility from co-catalyst is sometimes very important. Must always remember that exactly research was made. But this is enough to deeper in question. I think enough that we can write such equation and study it, calculate it from such system, where is used ion pair. But when we calculated polymerization rate by mechanism with free ions, when solvent we choose such that here is counter ion, not in such near, not so narrow, not so close with carbocation. That we must choose other equation without counter ion. But enough difficult at first, I think, and not necessarily complicated situation. And here it is directly for such ion pair, but not ionic bond. One must always remember this is very dangerous and very difficult to find conditions where that depends from solvent, that always stay here ion pair, or we can make any minutes tau is using for 5 minutes, for example, and finish this polycondensation process. Generally, I want to show what is differences with radical polymerization and step growth. Small to know about polymerization. Yes, understanding.
Yes, yes, and we hope here that you will get what you want in creation. So you get your independent and human and so on.
Thank you very much for your good wishes, and I get for to get for many Finnish friends and people. You accepted, you yes, our independence and wish for us in the future to be exactly independent. Thank you very much for that. I must continue and finish maybe more difficult or non-difficult question that our duty Ordnung ist Ordnung, als Deutsch sagt man. Yes. Polycondensation reactions. Here we can, to read polymerization process, I divide it into step reactions and chain reactions. Chain reactions we know now. That all these reactions was addition process, radical polymerization, ionic polymerization, cationic, anionic polymerization. All was as chain reactions. And is other very large division of polymerization process and polymer chemistry. This is step growth reactions, step reactions. But here is a short explained for you. You have a conspect, short summary. A little. Can you read step reactions and chain reactions? How you can understand it? No, step reactions are those in which the chain growth occurs slow. This is very important, slow. Chain polymerization takes place a rapid addition of olefin molecules to a growing chain, and rapid and slow. Slow or stepwise manner. It's very important differences with these both. It's attention. There's this polycondensation method, slowly and stepwise. And here is more clear, more sharply to say, two monomer molecules react to form a dimer. What here can we see? Monomer plus monomer. For example, bicarbonic acid and diol, the functional alcohol. Growing chain. Growing chain. Radical polymerization is just trying as radical, and here is end with their undead electron. And here I have other long growing chain by radical polymerization. No, once more it can possible to write, for example, such. And number 100 and number, here is not here. For example, 500 and here 1,000. Not a relationship, but approximately. What understanding such intermediate? And by polycondensation process, I have, for example, dimer and tetramer. This is E, for example, here it is here 5, no, pentamer. And J, for example, here is 10, decamer, maybe. And process. And I have E used growing, not chain, a step. I can step at all intermediates by condensation. And here I cannot, when polymerization is carried out, I cannot to get, for example, with such number, when I stop process, I cannot stop like this. I can stop, that was is usually for that system. Then usually system is with number, n 1,000. That's when we stop that means polymerization's degree, the same. Then as law for that kind of monomers is usually polymerization in that condition with number monomer units 5,000. When stopped reactions, all macromolecules must be 5,000 units. Only very small amount of polymer. Precipitation of process, or not such that I want to get, for example, with such long or with such long. That's not means that in short time when it starts reaction I can get that. A little more time when I use process I can get that. By chain reaction it's not possible. And after 2 hours I can get that. After 1 hour that. After 7 minutes that. Impossible. For chain reactions this is unusual. And for polymeric I can get polymers, called polymer, this is oligomer understanding. Polymer, this is poly, many, and oligos, small number. The Greek word. I stopped a reaction with, for example, 5 units. I can get polymers with 10 units. I can get with 100 units. Possible. Stop. This is dependent from polymerization time. Again, dependent that from conditions of polymerization, not time. Very important such basis. Here the chain growth takes place only at the ends of the few initiated chains. Yeah. Here is important that in radical polymerization we have a concentration of Bryce radicals. Such very few. Understanding? Like Bryce radicals we get from concentration from monomer, from initiator, very small number, and such is Bryce is about 10 minus 7 minus 9 mole per liter. And such begin. That means that are the few initiated chains. Initiated and grows very large. The monomer concentration decreases steadily throughout the reaction. Monomer concentration. And here, monomer concentration decrease instantaneously. Very quickly. The monomer concentration decreases steadily throughout the reaction. Dry polymer is formed rapidly from each initiated monomer. Dry polymer formed rapidly in time for formation macromolecules is about not 2 seconds. What is time for growing macromolecules? For example, 1 million average molecular weight, or with 100,000 degree of polymerization. And time is enough. And for step reactions, this time is necessarily hours and hours. The steply, slowly, stepwise, minor growth chain. Yes. Как он формулирует эти формулировки? At long reaction times may be an increase in the number of polymer molecules, but not in the molecular weight. That's good, I think, understanding. We can compare molecular weight with chain length, molecular number of molecules. This is with conversion understanding, with time of polymerization, with conducting of polymerization, increase number of polymer molecules, understanding, only number increase, but not molecular weight. Molecular weight remains the same, what is usual for that kind of process, for that kind of monomers, for that kind of condition of polymerization. Yes, at short, I want your attention to that. And now, I think, good, short, I won't show process. Now, maybe at first I want to show monomers, what is usually used for condensation or Stepson reactions, and after a little about concrete, more sharply about 1 or 2nd row. Units. Understanding? I wrote without this grammar, without and number, that is for polycondensation reactions, the number very different, not so as in polymerization in chain reactions, but so, there are always enough large, very large, and in polykondensation we sometimes in very cases, in many cases, we want to avoid oligomers with enough smaller number, 50, 100, for example, and other. But you will find misunderstanding. No, here is an example. For benzimidazoles. In other cases, unsaturated nitrogen to amidst groups, imidazoles. The aryl, this is understanding, I think. I can show it maybe, and you can find very easy from literature. Phenol formaldehyde oligomers, sometimes they are called as polymers, phenol formaldehyde polymers, but exactly true, that is without kind polymers, that is oligomers, by number of such phenyl, for example, here, and here wrote phenyl, and this formaldehyde. It is number of polycondensation. Average number is about 80 hundreds only. That we not call that is polymer. Usually, it's very difficult to say, but approximately can say that polymer properties begins when polymers then is about 500 number until, or not until, but in switching, in this range. This begin polymeric substance properties. When lower degree of polymerization conditions or properties is not so usually as so polymer. Polymer have any properties. For example, melting point is not so fixed as for other organic compounds. Polymer have not directly, sharply, exactly melting point. They have only smell and forgotten, but without exactly melting point. Only crystallized polymers, for example, stereoregular polymers, that very easy crystallized, they have exactly or sharply the melting point. That's this exception. Stereoregularly coordinated polymers. And other polymers have not. And elasticity and other properties for polymers is begin in such region of polymerization degree. And then we can call that is polymer. When we have phenolchromatic resins. This resins, not polymer. Interpretation polymer chemistry, this is we call oligomers. And we have phenol or other this situation is, you remember, ortho and para situation is active, remembering, then I use plus monomer, formaldehyde. I can get here reaction, very short, I think not so maybe good when I write in such. I think and then begin process. And this next monomer, this next phenol is wrapped, and we get such can get, for example, right, such, and set polymers, and that's phenol from a great resins, oligomers. Here CH2, what can you see? CH2. It's possible such, and it's possible CH2 and sometimes possible small. CH2 or CH2. Such way is possible. Proper organization is such. Thermoreactive polymer is possible by thermosetting. Polymers not melt after, not possible by molding process. We get yesterday to see as polypropylene, polyethylene, and other or polyesters and liners, thermoelastic, carbonic formaldehyde. Carbonic, urea, only English sometimes used what? Urea. Yes, not such here an example. We can write such. Urea is equal carbamide. Carbamide. Yes, and carbamide formaldehyde. The same reaction is possible here. For example, the change sheds, you get N CH2OH, and then you can condensation. Such reaction is catalyzed by laude, by bases or by acids. It's possible to by acid concentration. Possible by OH, by hydroxyl groups. On the resin setting polymers and linear polymers can to get. This is depending from catalysis, or this acid or this OH. In these cases, it was reaction this OH. Such. And linear, yes, that show carbamide formaldehyde. This is phenol formaldehyde and carbamide formaldehyde that begin as industrial product manufacturing enough before. Theoretical before First World War and practical after First World War. Industrial manufacturing for such kind of polymers and used they very often, and now in electrical technique in routine at all. And last two, melamine formaldehyde. Presence melamine, you remember such heterot cycle, maybe NH2, NH2, NH2. And if this formaldehyde, the same reactions. Can you see? Formaldehyde, such reaction. NH2, formaldehyde, NH2 here was formaldehyde, and begin growth condensation reaction. And last, polyurethanes, polyurethane molecules, it's very important polymers too. Maybe you can see practice in the laboratory. Here, short form schematically, we can CO, O, N, O, CO, NH, N, NH, N, CO. Yes, and now this principle was, and next I want to show a little more exactly, and anything's enough similar to this other polymeriization action. This polyesterification radical and reactivity. Such a radical is the same approximately. The same with carboxyl group, for example, assumption. This is Carozas and other chemists had to show that such error, for example, and OH, for example, or OH, and reactivity is the same. Theoretically, not always must be. A little to have induction influence, understanding. And other, maybe mesomeric effect, maybe conjugation effect. This is must be studying or must be account. But practical is not independent. The here side are independent of molecular size. This is very important for calculating simplify equations in mathematical form. When dependent, this is, you can understand it, when molecular weight 100, molecular weight 1000, and molecular weight 10,000. This is not so easy calculated rate of polymerization or polydensation, and other calculating processes. This is approximately, that is as rule, I depend on molecular size. That's each and every kind of, this was fine. And for example, 2, 3, for example. Deuteri or triti was marked, and then fine. Reaction, condensation. Such, not in such, very understanding, for example. There's easy understanding there. Yes? Yes, short. And here he says catalyst acids, maybe acids, many kinds of acids. Here is calcium acetate, maybe protonic acids as catalyzed. It's possible without catalyzed process. In summary, I wrote for you that's polyesterification reaction without catalyzing, without adding of acids. Then only that, for example, binaire. I can stop process while energetically and kinetically until other step, activation energy flowing, and here I can product with binaire or tetramer or elements removed, and by polymerization process, activation energy is not so larger, but process begin after induction process, moment or period indication, and then polymerization reaction progress is very quickly, and I cannot stop the reaction. Reaction is possible to stop, but I cannot get stepwise monomer, polymers. And after a short time, by this activation energy, and polymer can remove this exactly polymer arrangement weight for such polymer. In 1 or 2 seconds is finished. Such process is such level of activation energy. And that is Gibbs thermodynamical second law, as you remember, and thermodynamical energy is a time mean. We know law must be smaller as 0, and changes of entropy must be smaller as 0. This means minus and minus. Here is must minus 9. Begin for decarbonization. Delta dash minus. So, right. And how is this entropy? Is 2 minus. How it means about entropy by polymerization? What is larger entropy or 3 steps? For monomer or for polymer? What is smaller entropy in absolute meaning? What is smaller? Entropy 0 by what condition is at all? Yes. Or by polymerization, for example, we have monomer, and we have polymer. This entropy in absolute is larger, this entropy polymer is monomer. Understanding why monomer is enough rib in brown monomers in vessels and polymers, for example. Entropy is small. Yes. Thank you very much. I wanted for you brilliant future. And thank you for your attention, for your hospitality, for your kindness and presence, and all what you showed for me in that short time when we got our lectures and our connection with you. Thank you very much. Remember all.
Not to discuss so deep about mechanism of reactions of polymerization. You had 20 hours about mechanism, but to discuss some other aspects of polymer chemistry, of polymerization reactions, some technical aspects, influence of various factors to polymerization, and also most important properties on molecular level. What are properties, really properties of macromolecules, not as polymer, as plastic, but properties of material which contain macromolecules, very large molecules. Really, what are properties? And today we will deal with technical aspects of polymerization processes. Of such processes you discussed earlier with Professor Bajoro, but now we will deal how technically possible to carry out polymerization, radical polymerization, or polymeriization, or ionic polymerization, and how it's possible to regulate these processes, and also regulate this way kinetics of polymerization, and of course some properties of final compounds of polymers. And also I would like to say first that we discussed on Saturday, we will change a few programs for these 12 hours, and we will have also demonstration. So next time, next Thursday, will be not lecture for you, but will be demonstration. Will be at the same time at 5 p.m. And I think you have to collect here, and then I will take you to small laboratory where I usually do synthesis. It will be some special synthesis of polycarbonate. This is a very usual way to make polycarbonates, such kind of way as I will show you. But I think you can see only now because is not possible to use by students by their hands, because you have to use phosgene gas. You know, it's very dangerous, and I think now there are in Finland only very few places where use phosgene. And now I have this phosgene because I use for my research here. So you have only this possibility to see. And maybe you will have, I don't know, maybe next semester or next year some laboratory works more on polymer chemistry. I don't know, because now there are some arrangements here to prepare such. So we will have, I think, about 2 hours or maybe a few more. But then we can calculate how it is, because we will be as long as polymer will be ready, I think. Then to see how it's possible to separate them. technical aspects of polymerization processes. Now you know main methods to make polymers: radical polymerization, ionic polymerization, stereospecific polymerization, polycondensation, and you know that in many cases it's possible to use not one but some methods to polymerize same monomers. For example, styrene can be polymerized by radical polymerization or by anionic polymerization. Same, some other monomers by radical and by stereospecific. For example, ethylene you can polymerize under pressure by radical polymerization, or you can use Ziegler-Natta catalysis to achieve stereoregular polymers. But also, if maybe a most easy way, also in industrial scale, to polymerize using radical catalyst. You have not to use very special condition. There are not so exact requirements for purity of monomers and of whole system, because for ionic polymerization you have to be no water traces at all. You have to be very inert atmosphere and so on. And it's of course more cheaper to make radical polymerization. And that's why there are quite many possibilities, quite many methods how to polymerize monomers using